Okay, good afternoon, everyone, and welcome to the final talk of the session. Our speaker today is Sarah Lee, who is an undergraduate at the University of Dalhousie, and she has survived the hurricane to give us the talk today. So I hope you all are suitably impressed. Sarah, please take it away.
Well, thank you, Dr. Duncan, for introducing me. And today I'm going to talk about the integral Clifford plus T circuits composed of NOT, C0, Toffoli, and Hadamard gate tensor with itself. This is a joint work with Julian Ross and Peter Selinger. Our work is motivated by the exact synthesis problem in quantum computation. We use number theory and algebraic tools to characterize a group of Clifford plus T integral Clifford plus T circuits in purely algebraic terms. So we start by defining Z1/2 as a ring of dyadic fractions whose denominator here is a power of 2. And we define O and Z1/2 as the group of orthogonal matrices over this ring, and we call them as the group of orthogonal dyadic matrices. In 2020, Amy et al. Said that there is a correspondence between the group of orthogonal dyadic matrices and the group of integral Clifford plus T circuits. In many quantum algorithms, the integral Clifford plus T circuits play a very important role, and people ask a lot of questions about them. For example, given an orthogonal dyadic matrix, how to find a circuit for it? And in particular, how do we ensure that we find a circuit that is as short or small as possible? So today we're going to study these operators in details. Let me start by telling you some well-known gates. For example, the NOT gate corresponds to a 2x2 matrix. The -1 gate is actually a scalar and will be used very nicely in the future algorithm. And the Hadamard gate and K is a shorthand for Hadamard gate tensor with itself. And all of those operators will be used as prototypes to define n-level operator. So we'll start by defining two-level operator precisely. Suppose you're given a 2x2 matrix, U, with x11, x12, x21, and x22. So we're defining U alpha beta as a larger matrix, and the intent of this is for it to act precisely as U on specified element of the column vector V here. So as you can see, it is going to act as U on the alpha and beta element, and it will act trivially on every other element. So for example, let's say we have a NOT gate, and we're trying to create x24 by embedding the NOT gate inside of a 4x4 identity matrix. So essentially what we're doing is we're filling in like corresponding positions with elements from X while keeping everything else unchanged, to the effect that this x24 will act trivially on the first and the third element and will act exactly as a NOT gate on the second and the fourth element, which it will swap these two elements. And this can be verified just numerically. And similarly, we can create a four-level operator by embedding a 4x4 matrix U into an n by n identity matrix. So for example, let's say we have a K gate as mentioned before, and we're now creating x1, 2, 4, 6 in the context of a 6x6 identity matrix. So what we do is we're filling in corresponding positions in this 6x6 identity matrix with elements from K while keeping everything else unchanged, as you can see highlighted in red here, and such that K1, 2, 4, 6 will act exactly like K on the first, second, the fourth, and the sixth element. So we'll perform linear transformation on this four elements, and it will act nothing on the third and the fifth element. Similarly, we can create one-level operator using this embedding idea. And now our work is interested in a generating set for the group of orthogonal dyadic matrices. And we define this generating set as G. And it is composed of -1 alpha, X alpha beta, and K alpha beta gamma delta. And this is actually established by Amy et al. In their 2020 paper. And they said that if M is a unitary n by n matrix, then M is an orthogonal dyadic matrix if and only if it can be written as a product of elements of our generating set. So to prove this theorem, we want to start from one direction. So suppose we're given an operator and it can be written as a product of generators. And since we know that G lies inside of our group and group is closed under multiplication, so we know that this operator M is indeed inside of this group. But for the other direction, we want to show that for every orthogonal dyadic matrix, we're able to find the decomposition over the generating set. So this is not trivial. What we can do is to devise an exact synthesis algorithm that will take an input as the matrix and will iteratively output syllables. And here the syllables are just composed of generators. So indeed, we're actually implying the reverse engineering idea. What we do is our algorithm will look at this input matrix and it will start from the rightmost column and it will fix the column vector to the corresponding basis vector. And then we'll move on to the next column all the way till it's reached to the left-hand side of this matrix, input matrix. And to the end, it will turn this input matrix into an identity matrix. And for every iteration, the algorithm will keep outputting generators. And the sequence of these generators will have this form GL to G1. And since our generators is self-inverse in the context, this means if we apply the inverse on this output sequence, then we're able to find the decomposition of the input matrix. And since this is for arbitrary operator, then we prove the theorem. So this, this theorem basically revealed the characterization of the integral Clifford plus T circuits by this following two corollary and theorems. Amy et al. In their paper said, G can be exactly represented by the integral Clifford plus T circuits using at most one clean ancilla. So recalling the theorem before, there's a correspondence between the group of orthogonal dyadic matrices and the operators over the generating set G. Along with this corollary together, we can prove that there is a correspondence between the group of orthogonal dyadic matrices and the group of integral Clifford plus T circuits. So essentially, we found the generators of our group, and we're going to use these generators and the exact synthesis algorithm to find the relations for our group, which will be the contribution of our paper. So in order to better understand this group structure, we want to visualize it using the graph. So we define a graph, which is essentially a reminiscent of the Cayley graph by defining every vertex to be a group element, as you can see here. Since there are infinitely many group elements, there will be infinitely many states. So note that here we'll use states, operators, matrices interchangeably. We define an edge to be a sequence of generators. So for example, let's say you have state S4 and you want to go from S4 to S3. So what we do is applying F, this generators, sequence of generators to S4, and you can consider this is performing a group operation. And then this means S4 is equal to S3. And we define a cycle to be relations. It means, suppose if we have S4 as a starting point and S3 as the destination. As you can see, GE and F are two paths, although they look different, but if you examine the operation here, they do the same job. They start from the same point and end at the same destination. Therefore, we say that EG is equal to F, meaning that they correspond to the same operation. They do the same job. And because our exact synthesis algorithm is deterministic, it means that it will give a canonical path from every group element to the identity matrix. So if you can just imagine our the exact synthesis algorithm is walking inside of our graph, and for an arbitrary group element is going to find a canonical path and will send this element all the way to the identity. And this will become very useful for us to find a finite set of relations for this group. So before moving forward, let me clarify a few notations. So the first one is a word. So we define it to be a sequence of generators. You can consider it as a concatenation of letters where every letter in here, GQ to G1, is essentially correspond to a generators of our generating set G. And each operator has a unique normal form, which is the word output by the exact synthesis algorithm. And we interpret the word in terms of their matrix representation. So if you look at the corresponding matrix of G, what we can do is by doing the matrix multiplication of every matrix correspond to every generator, GQ to G1. So we define two words to be semantically equivalent if they have the same meaning or they do the same job to be G tilde F. So basically, if you calculate the matrix representation of G and the matrix representation of F, then they are the same. So now let's consider two scenarios, well, actually one scenario. So we have two circuits, C1 and C2. So C1 is composed of three operators. So we have X12, X34, and X12. And we have C2 composed of only one operator. So we wonder whether these two circuits have the same meaning or if they do the same job. So one way to do it is just by direct computation. We calculate the matrix for C1 and the matrix for C2, and we compare them. But imagining if we're dealing with 30-qubit circuits, then our matrix multiplication will become exponentially large, which we don't want to do that if we have a large number of qubits. So what we want to do is, if there's a way that we can rewrite C1 into an equivalent form, but it may be simpler or maybe closer to the form that C2 has. So if you observe C1 from our basic relation table, we know that when two operators have disjoint indices, for example, x34, x12, they can be commuted. So we can just swap them and we'll get 2x12 together. And because we know that 2x12 is equivalent to an identity matrix, so we just put it there, which will lead us to x34. And since throughout this rewriting process, the meaning of our operator is not changed. So we know that essentially C1 is the same as C2. They have the same meaning. So this gives us some inspiration about if we are hoping to find the semantic equivalence between two circuits or two words, maybe we want to define a syntactic notation just so we can, don't need to get into the computational details. So now we're defining a new set of relations called syntactic equivalent relations by using a basic set of relations. So what we want to do is, let's say we have two words, G and F, then our relation will be able to, and we know we'll be able to apply this finitely many rewrite rules to write G into its equivalent form. And this will allow us to define the smallest congruent relations on the words containing these relations. So here by congruence, we mean that if you give me a pair of equivalent relation, let's say anything, then I'm able to create a new set, a new pair of equivalent relations out of it. So this potentially allows us to extend our finitely many relations to infinitely many relations. Okay, so our next question is, how can we use syntactic relations and semantic relations interchangeably, which is captured by this following theorem. So let G and F be words over the generating set of our group. Then G and F are semantically equivalent if and only if they are syntactically equivalent. So in order to prove the soundness, so let's suppose if we claim that two words are syntactically equivalent. So if we take any relations from our table, we want to show that they are reasonable, they are sound. So how we prove it is just by computing the matrix representation on the left-hand side and the matrix representation on the right-hand side and just compare them. And this will complete the proof. But for the other direction, if we know that two words are semantically equivalent, basically we want to show there exists a finite sequence of rewriting rules that will allow us to write G into F, which prove the completeness, meaning that our set of syntactic relations table captures the entire orthogonal dyadic operators group in terms of its semantic meaning. Okay, so let me explain the proof idea. So basically, if two words are semantically equivalent, then they correspond to the same normal form. And if we can reduce an arbitrary path to its corresponding normal form using the syntactic relations that we have, then this implies completeness. And if you look at just the following diagram here, where S is an arbitrary state in our group, then let G and F be two arbitrary simple paths, and M is the unique normal path. Then if we can show G and M are syntactically equivalent, M and F are syntactically equivalent, then we can show that G and F are syntactically equivalent, which is captured by this diagram here. But note that essentially we're still dealing with infinitely many cases because there will be infinitely many states in the graph. What we want to do is by using induction to leverage finitely many syntactic relations such that an arbitrary path can be rewritten into its equivalent canonical path. And indeed, in our research, we ended up finding a finite set of relations, as you can see here, and there are in total 32 of them. Okay, now you may wonder, so how do we prove the completeness exactly, and how do we find these relations? So let me start by telling you the first lemma. So suppose we have an arbitrary state S, and G is just a simple path from S to I, and M is a normal path from S to I. We want to show that this diagram commutes, meaning that we can write G being equivalent to M. So note that here, this simple path G can be arbitrary length. So it means we're essentially still dealing with infinitely many cases. So in order to simplify the discussion, we want to proceed by induction on the length of G by taking out one single edge of length 1, which will lead us to this diagram here. As you can see, G prime will have length shorter than the previous G, which will allow us to perform induction hypothesis on this subgraph. So our problem now is reduced to solving this diagram. We want to show this diagram commute, which is captured by the following lemma. It says, let S be an arbitrary state and S will be sent to R by the single simple edge, and let N and M be two normal edges coming out of S and R respectively. Then we want to show this diagram commute. Note that here, we still have not a lot of information about the normal edge N. It can be arbitrarily long. So in order to further simplify our discussion, what we can do is to perform induction on the level of S. Note that here, the level of S just measure the distance between our input matrix S to the identity matrix throughout the process of our exact synthesis algorithm. So the higher the level, the longer the normal path it will end up with. So basically, there's a correspondence between the length of the normal edge and the level of S. So this idea is captured by this following diagram here. As you can see, if we take out one single normal edge from the previous N, then now we end up with this N naught of shorter length. So if we can find an appropriate induction hypothesis condition, then we can like reduce our problem to solve basically this diagram. So how do we do that? So suppose we can find a path from T naught to TK where every intermediary state between T naught to TK will have levels strictly lower than the level of S, then it means that for every triangular cell to start with, we have a normal edge of shorter length than the previous one, and then we have the satisfying states level, then we're able to apply induction hypothesis. This means we further reduce our problem to solve this following diagram. And this is actually the most important lemma in our work. It is called the main lemma, and this will lead us to find our relations. So let me define this lemma precisely. So suppose you are given an arbitrary state S in your group, and let N be the unique single normal edge coming out of S, and let G be a single simple edge. So as you can see, once S is fixed and G is fixed, then you will uniquely have this state R. And since for every state there's a unique normal path to it, then we know that this N is also unique to us. So what we want to do is want to prove that this diagram commutes, meaning that there exists a path from T to Q where every intermediary state between T and Q will have level strictly lower than the level of S. And in order to prove this main lemma, what we can do is by observing this diagram and see that, oh, once S is determined, then N is uniquely determined, as I explained before. And once G is determined, then R is determined. So basically, if we can perform case distinctions on a pair S and G, then we're able to cover all possible cases in our group, which will complete the case distinction. And while we're doing this case distinction for every case, we'll proceed by trial and error, and that will allow us to find our relation. All right, so now let me wrap up with some open questions. So to start with, we hope to improve the complexity of the synthesis algorithm. So for now, we're only looking at one column at a time. So we're wondering, instead of looking at the matrix locally, are we able to take a global view of our matrix by looking at some metric so we can have more informed information about what generators to output for every iteration? And this may lead us to have a shorter decomposition of every input matrix. And on the other hand, we hope to interpret our syntactic relations in terms of quantum circuit equivalent relations. So if you look at our table, like our relation right now are pretty abstract, but if we can understand them better in terms of the integral Clifford plus T circuit, then it will open doors to future optimization. Moreover, we haven't addressed the issue whether one relation is the consequence of the other. And if we can answer this question, then we are able to remove duplicate relations from our 32 relation table, and we'll find a minimal set of syntactic relations. Finally, we hope to extend our approach to find syntactic relations for other restricted Clifford plus T matrix groups, such as the Gaussian and imaginary Clifford plus T circuits. That's it. Thank you.
Thank you very much, Sarah.
Thank you.
There are a couple of questions in the Slack, but I wanted to ask
Okay.
a little clarification before we go on to that, which was that I thought that at the beginning of your talk, you had said that the generators were this relatively common set of gates, the control Z, the double Hadamard, etc., etc.
Yeah.
So, and then you said at the end that your relations were not circuit relations. So can you close that gap?
Oh, yes. Well, first of all, thank you for the question. It's a very good question. So as I mentioned before, there is a correspondence between our circuit and our numeric characterization. But the thing is, if you, well, let me share the screen with you guys so you could see this more clearly, because I think it's better to illustrate it with an example. Okay, so let's go back to this relation table. Okay, so now, oops. Okay, so now let's say if we just look at this one here, disjoint indices, we have two operators with disjoint indices commute. K, A, B, C, D commute with X, J, K, where they don't intersect. But how do you know which gates it corresponds to? Like, for example, if I give you K 1, 2, 3, 4, X 5, 6, could you write it into integral Clifford plus circuit, Clifford plus T circuit very easily? The answer is it depends. Sometimes we'll have like an easier rewriting process, but sometimes we really have to like try all different kinds of combinations. So if there's a way for us to utilize these relations better, then that would be more helpful for us to understand the integral Clifford plus T circuit relations. Does that make sense?
That's a perfect explanation. Thank you. Thank you.
No problem.
Question from Benoit Valéron, who asks, is it reasonable to summarize this exact synthesis algorithm as saying that the householder decomposition can produce Clifford plus T circuits if the matrix is in Z of a half? That might not be very easy to understand when just said verbally, but
sorry, could you repeat the question?
So I will simply quote, would this be a reasonable takeout of the exact synthesis algorithm? Householder decomposition can produce Clifford plus T circuits if the matrix is in Z of 1 over 2.
Okay, that's a good question. So basically, you need to consider the dimension of your matrix, because as we know, whenever we are adding 1 qubit, we're going to like increase the dimension by 2 in terms of the matrix correspondence. So like you cannot just say any any orthogonal dyadic matrix correspond to a circuit over the integral Clifford plus T gate set, because maybe the dimension is not valid. So you have to, restrict yourself to the 2 to the power of n by 2 to the power of n orthogonal dyadic matrices to have this conclusion. I hope I'm right.
Okay, and I will give the final question to Alec Edgington, who asks, is anything known about the computational power of this class of unitaries?
Computational powers? What? Could you explain a little bit more what is computational power?
As in, is this a universal class? Is it more powerful than the Cliffords? Where does it sit?
Oh, okay. Yeah, that's a very good question. So, well, as we know, we're actually dealing with the group over the real number. So we know that they are not universal, which will become problematic. Well, it will not be as useful as, integral, like a universal quantum gate sets. However, as we mentioned, if you add one clean ancilla into the circuits, then you are able to find a universal group, which will become very handy in the fault-tolerant quantum computation. So I think it's good. Like the computational power is good.
Okay, I think we should draw halt to this session now. So I want to thank Sarah for the very interesting talk and all the other speakers today for their contributions.